Good afternoon to all of you. I am Thierry Vastio from Interface Concept. And today I would like to present an R&D program on shape recognition algorithms. In this program, new, fast, parallel shape recognition algorithms were developed. They were FPGA co-processed accelerated, and in hybrid VPX high-performance embedded computer systems. This program was led by Interface Concept, together with the EBO University of Brittany. So in this program, the first part of this program was about developing new innovative implementation of fast Fourier transforms, FFTs, and discrete cosine transforms, DCTs, in FPGAs. And the goal was to reduce the execution time of the transform, and also to decrease the FPGA resources to run them. What were the achievements of this first part of this first development effort? To measure the improvement, we have used a ratio, and the ratio was between the throughput of the transform on a continuous mode and the FPGA resources in terms of slices. So for a 256 FFT, point FFT, we have improved the ratio by a factor of 5 compared to the IP on the market, which is not too bad. And for a 16K FFT, the improvement has been a factor of 4. So in terms of power consumption, and to show the power efficiency of these solutions, we have achieved the following figures in Virtex 6 FPGA, SX315T, again on a continuous mode, of course. And the achievement was 100 milliwatts for 1K FFT. It was 150 milliwatts on a 4K FFT, and 50 milliwatts in a 64 points FFT. You have here a slide showing the improvement made, function of the size of the FFT, again in front of other IP on the market. The second part of this program has been to use these new implementation of transforms to build, let's say, fast shape recognition algorithm. So what we do here is digital correlation between a target image and a reference image. And we do that in the following way. Using a 2D FFT, we get the spectrum of the two images. We multiply the two spectrums, and we carry out an inverse transform to get the digital correlation. So it's a good way to use the high-speed execution of the transform in FPGAs. So then what we do is we take the correlation peak, normalized to the correlation plan, and we decide that the two images are the same if the correlation peak is above a defined threshold. So what were the achievements with this? We were able, building let's say a practical VPX system, we were able to put on a Virtex 7 FPGA, VX690T. We are able to put 30 correlation architectures as the one described above. So, and each correlation architecture was able to process 4,000 images per second. So we do that using our, we will see later, our front-end processing boards. So it means that in a Virtex 7 FPGA, you can process and decide on 120,000 images per second. So now we build a practical 6U VPX system using these algorithms. And we use here our own designs. In this case, the IC-FEB VPX 6B, which is a front-end processing board. Each board having two Virtex 7 FPGAs. And to feed the FPGAs with images, we have used Vita 57.4 FMC, optical FMC, using the transceivers of Reflex Photonics. So these transceivers, these FMCs have 12 full duplex optical links, each link going up to 28 gigabit per second, depending on the speed grade of the FPGA. So now, building a full VPX system, we put 5 of these boards in a system together with the optical FMCs, and with this kind of system, we were able to process 1.2 million images per second. So you see the power of this kind of approach. Now, if we look at the next generation of FPGAs, and especially the ultra-scale plus of Xilinx, with this, especially with the VU13P, you see that you can get here a tremendous amount of power. So, for instance, in these FPGAs, you have 3.5 million logic cells. So it's a factor of 5 compared to the Virtex 7 we discussed before, and up to 12K DSP slices, and this is a factor of 4. In this kind of FPGA, you have 128 32.25 gigabit per second transceivers. So it means that in an FPGA like this, it is a multi-terabit per second throughput. You have also integrated 100G MAC blocks and PCI Express Gen 3 cores. You have also, and this is very important, advanced clock management or distributed clock buffers. And this allows us to put in parallel a lot of blocks, and to have very wide buses, typically 2058 bits. And this is exactly what we need in this kind of application. So interface concept is currently developing boards using these new families of family of FPGAs, and we take benefit, of course, from the outstanding performances of these FPGAs. So, and again, we used during all this program, we have used optical links, and in this case, in the final implementation, we have used this Vita 57.4 FMC developed in partnership with Reflex Photonics, and with you can see here this FMC with its two 12 optical links transceivers, RX and TX. And we are circulating this FMC to show you the technology.